Okay, let's talk about section 4.4, monotone functions and the inverse function theorem. Okay, so first let's we review the definition of the monotone functions. So definition, let E be a non-empty subset of R, and F from E to R be a function, right? And first one, F is set to be increasing, crescendo, or respectively strictly increasing. On E, if and only if x1, x2 in E and x1 less than x2 imply fx1 less than or equal to fx2. Okay, so this condition corresponds to be increasing. And if we put the parentheses respectively, fx1 less than fx2, then this is called strictly increasing. It's our common definition. So here, there's some other set of the writing. So sometimes we just call this increasing. You may see that this one is called increasing, and this one is called non-decreasing. Okay, so this is another set of the notation. You may see non-decreasing. Non-decreasing means less than or equal to. And for other textbook, when they say increasing, they really mean the strictly increasing. So every time when you check this increasing, decreasing words, you have to make sure if they include equal sign or not. Sometimes they don't bother, but sometimes they do bother. Okay, so just make sure you use the right explanation about increasing and strictly increasing. But not regularly strictly increasing always corresponds to this, but increasing may have different meaning for different textbook. They are both commonly exist. And similarly, f is said to be decreasing or respectively, respectively strictly decreasing on E if and only if x1, x2 in E and x1 less than x2 imply fx1 is greater than or equal to fx2. So here is always x1 less than x2, but this one you change it from less than or equal to be greater than or equal to, or respectively fx1 is strictly greater than fx2. This is a strictly decreasing. So large input has a smaller output. It's a decreasing, right? Again, this is called non-increasing sometimes. When you use non-increasing, it corresponds to this one is called decreasing. Okay. And third one, f is set to be monotone. Or respectively strictly monotone. On E, if and only if f is either decreasing or increasing, respectively either strictly decreasing or strictly increasing. Okay, monotone just a common word for this increasing, decreasing. On E, of course, on E. Okay, so we have increasing, decreasing, and monotone. Well, of course, we all know that this is a special property for small class of functions. Not every function will be monotone, right? And for example, fx equal to x squared is not monotone. On its domain, but if you restrict it to a smaller domain, a subdomain, it is increasing over the domain 0 to infinity and decreasing over the negative infinity to 0, right? So once you change the domain, you will have the monotone. All right. Okay. So this is the review of common definitions. Now let's see how do we connect the derivative of the derivative function to the monotone property. This is also the common property which we will review. So 4.24 theorem. Suppose that AB in R with A is not equal to B, that F is continuous on a closed interval AB, and that F is differentiable on the open interval AB. So this is exactly the condition of a mean-value theorem, right? Continuous over closed interval, differentiable over open interval. Because we write A and B, so let's just assume A is strictly less than B. The other way you have to write BA, not AB, right? Okay. So with this condition, then what we have? We have first, if f prime of x is greater than 0, or respectively, f prime of x is less than 0 for all x in AB. So here we do not just require it to be positive or negative for a single point. It has to be positive or negative over the whole open interval. Then f is strictly increasing or respectively strictly decreasing. On the closed interval AB. Right, strictly decreasing on the closed interval. And the second, if f prime of x is equal to 0 for all x in the open interval AB, then f is constant on AB, right? F is constant on AB. Okay, so this is exactly the application of the mean value theorem. Okay, so let's try to prove. Let's assume the f prime of x for the part 1. Let's assume f prime of x is strictly less than 0 for all x in AB. Because in the proof, in the textbook, they choose f prime of x is greater than 0. Now let's choose f prime of x is less than 0. Okay, so for any a less than or equal to x1 less than x2 less than or equal to b, for any 2 points x1, x2 in the closed interval A and B, and x1 is less than x2, then what we can say, we have that f is continuous on the closed interval x1, x2, and the differentiable on the open interval x1, x2, then by the mean value theorem, mean value theorem for just one function. Usually when we say mean value theorem, we don't include that 2-function version. That is called Cauchy mean value theorem. Okay, that's a strong version, but here we just use this regular version. By the mean value theorem, there is a C in the open interval x1, x2, such that fx2 minus fx1 over x2 minus x1 is equal to f prime of c, but we know f prime of c is here less than 0. F prime of c is less than 0, and we also know that x2 minus x1 is positive. So fx2 minus fx1 is equal to f prime of c times x2 minus x1 is negative, so f of x2 is less than f of x1 for arbitrary x1, x2. So f is decreasing, strictly decreasing. F is strictly decreasing, right? So just change it to be negative, and the book in the textbook it's a positive. It doesn't matter. Positive. This is positive. Then this is strictly increasing, right? So we know this result in the calculus, but here we just want to confirm it with a solid proof. We don't just take it for granted, because this is analysis, not calculus. And the second part, we're going to show that f is constant. Well, assume. Okay, so assume that f is not constant on the interval AB. If there's not a constant, definitely there are two values. So there are C and D, two values happened, of course, at 2 points. C and D, let's write CD in AB with, let's say C is not equal to, C is less than D and FC is not equal to FD. Okay? C is less than D is used to form the interval. Otherwise, I can just say C is not equal to D. Okay? Then on the interval C and D, F is continuous and F is differentiable on the open interval C and D. And by the mean value theorem, we have Fd minus Fc over D minus C is equal to, we have a F and F in CD such that, not Fg, we already use GH, let's use X and X. We have an X in C and D such that Fd minus Fc over D minus C is equal to F prime of X. Fd minus Fc, Fd is not equal to Fc. So F prime of X is not equal to 0. But this contradicts to the hypothesis, the condition that F prime of X is equal to 0 for all X in A and B. Well, this X is in CD, of course X is in AB, right? So F has to be constant. F is constant on AB, closed. F is constant on AB. Right? So once you have a zero derivative, then it's always constant. Right? Once you have zero derivative, it's always constant. And this result comes from the mean value theorem, the crucial mean value theorem. All right. Next, we want to generalize this the second part of 4.24 to a general case. So the general case will be the remark. If F and G are continuous, on a degenerate, non-degenerate, degenerate we will not talk about, non-degenerate interval A and B. We really have an interval AB. A is less than B. And differentiable on the open interval A and B. And F prime of X is equal to G prime of X for all X in the open interval AB. Then F minus G is constant on AB. Okay? Why we say this is a generalization? It's because here you can consider 0 as a derivative of arbitrary constant. Right? 0 is a derivative arbitrary constant function. So F prime of x is equal to the derivative of a constant function. So f minus a constant function is a constant. So f is a constant, right? So, well, this remark is a truly simple observation. We just apply 4.24 part 2 to the function f minus g, and you will get it. F minus g has derivative 0 because the derivative has difference rule. F minus g has derivative 0, so f minus g is a constant. So f minus, yeah, that's it. And this is a reason we discussed the mean value theorem right before the anti-differentiation. Okay? Because anti-differentiation requires this property. All right, so that's a review. This is whole thing is just a review, except this part. This part we give solid proof, even though the conclusion we know it for a long time. Okay. So now let's connect the stuff to the inverse function. So inverse function, we talk about the real function. F is a real function. Real variable, real valued function. A real function, f has inverse. If f has inverse, has an inverse function, then we know that the graph of y equal to f inverse of x is symmetric, or reflected is symmetric to the graph of y equal to fx with respect to the line y equal to x, right? This is a common thing. And we can see that f inverse is as smooth as f. You just flip this graph. You do not break it or bend it. So if the original graph is smooth, the new graph will be also smooth, right? Well, we will see. Okay, now let's see the solid proof. We got the geometric idea, but now let's see the solid proof. So to have an inverse function, it must be one-to-one. If f is one-to-one and continuous, on an interval I, then f is strictly monotone on I. So continuous one-to-one implies strictly monotone, either strictly positive or strictly increasing or strictly decreasing. And f, okay, so this is the first conclusion. It's strictly monotone. Then f inverse is continuous and strictly monotone. On the fi. Because it's strictly monotone, it's continuous. So this is an interval. You will see that this is an interval. It maps. To be an interval, you have to use intermediate value theorem, IVT. To be interval, you need IVT. Okay. Okay. Now let's see the proof. let's assume, well, of course, we always discuss a non-degenerate interval, and that only in that case it makes sense. Otherwise, it doesn't make sense. If you just have one point, you can say it is always monotone, right? So assume I is non-degenerate. Non-degenerate. If I is non-degenerate, it will contain at least 2 points. So here we don't say it is open or closed, so I have no idea if it contains a boundary point or not. So that's why I cannot write it boundary point. But it will contain 2 points. When it contains 2 points, we are going to study the interval over that small neighbor, a small interval. So we are going to study the property over that small small interval. So like this, AB containing I, closed interval AB containing I. Okay, well, I assume A is less than B, so I write this. So monotone we are going to have positive, increasing, decreasing, but we want to show it is monotone, but so far we don't know if it's monotone, but F is 1 to 1. A is less than B, F is 1 to 1, so we have either FA is less than FB or FA is greater than FB. Okay, so either less than FB or greater than FB. Okay, so that's 2 possibilities. So let's see. If this F is not monotone, how do we prove? If F is not monotone, not strictly monotone, on I. If it's not strictly monotone on I, then there is a pair not pair, a triple A, B, C in I such that we do have the condition about A less than B less than C, but FC does not lie in or lie between FA and FB. So basically, we want to say that for a pair, it is increasing. For the other pair, it's a decreasing. So, or you can find such this pair, or the other way, so that you can either get it this way or you get this way, so that the function by this it is not monotone, right? If you always have this, it's increasing, or if you always have this is decreasing. But for those 2 cases, FC is always between FA and FB. This is FC. But this way, like the not broken, the banded version is not monotone. So that's what they say. FC does not lie between FA and FB. Okay. Okay, so let's see. FA is not equal to FB. So for those 3 values, there's no pairs on the same level. So we will have what? You have 3 values, right? You have 3 values. FC does not lie between FA and FB. Then we have either FA lies between FC and FB, FB or FB lies between FC and FA. Okay, so you do have the order. You do have the order. So either this way or that way. Either FC is above both of them or FC is below both of them. FC is not between, right? Either above or below. If it's above, you will get 1 point between them. Or if it's below, you still get 1 point between them. Right? That's what they say. FA lies between FCFB or FB lies between FCFB. FB lies between FCFA. But these two cases are symmetric. So assume that FB lies between FC and FA or FA and FC. Now remember here, this theorem does not require differentiability, so we don't know if a function is differentiable or not. We only have continuity. Continuous function has intermediate value theorem. So this value is between FA and FC. A is less than C. So F is continuous over the closed interval AC, and FB lies between FA and FC by the IVT intermediate value theorem. There is a D in AC such that FD is equal to FB. FD is equal to FB, right? That's an intermediate value theorem. But this is not good because it contradicts to the one-to-one condition. We couldn't have a one-to-one condition. Actually, from here you will see that once you have such case, you violate a one-to-one condition. Okay, so it implies this cannot happen, FC cannot happen. This implies this if it is not strictly monotone. If it's not strictly monotone, you can always go through this. So it implies F is strictly monotone. It's one-to-one, so it is either, it has to be strict. There's no equal case. There's no equal case. Okay, so let's okay, actually from this part of the proof, we can see that if CD in I we can show that F inverse, function of inverse is strictly increasing. Strictly monotone, not increase, strictly monotone. So well, not FCD. Let's assume it is here we first show it is strictly monotone. How do we show it is strictly monotone? Let's assume contrary. So suppose F inverse is, well, let me see. We're going to show F inverse is strictly monotone. Here, we already know that F is strictly monotone. There's two cases about monotonicity. So let's assume that F is strictly, here in the book it is increasing, now let's say decreasing. Assume that F original function is strictly decreasing on I. We want to show F inverse is also strictly decreasing. Okay, we want to show it is also strictly decreasing. Let's assume, okay, so assume that F inverse is not strictly decreasing. Strictly. Not strictly decreasing, it means there are y1 less than y2 in I with, it's not strictly decreasing, with F inverse of y1 is greater than, not. If it's greater than, it will be right, less than F inverse of y2. Right? This is not strictly decreasing. Actually, it could be less than or equal to. Strictly decreasing is greater, not less than or equal to, but because F and F inverse are both 1 to 1, so there's no equal case. So you have only the less case, less than case. Okay, so let's call this x1, this x2. x1 is F inverse of y1, x2 is F inverse of y2. So by definition, we have fx1 equal to y1, fx2 is equal to y2, okay, and x1, x2 with this condition, x1 less than x2, x1 less than x2, x1 less than x2, f is decreasing, strictly decreasing. So fx1 strictly it will be greater than fx2, but fx1 is y1, fx2 is y2, so y1 is greater than y2. This is contradiction. Hence, f inverse of y is strictly decreasing. Strictly decreasing. Okay, so if original function f is strictly decreasing, then f inverse is strictly decreasing. If original function is strictly increasing, f inverse is strictly increasing. This reflection does not change the monotonicity. Okay, so with this strictly decreasing, let's consider this case, because in the book they consider f is strictly increasing all the time. Now let's consider this f inverse is strictly decreasing. F inverse is strictly decreasing for CD in I, C less than D. Then by the intermediate value theorem, f maps CD to FD, FC. Remember, this is a strictly decreasing. You have to flip the order, flip FD and FC. This is exactly the intermediate value theorem when we have the strict monotone. Okay, so this, for every pair you will have such a thing. So this implies that Fi is an interval. Well, it depends on, so far you have to flip this. If you have the endpoints, you have to switch the order F, D, F, C from C and D. Okay? Okay, so we do have an interval. We already have the, what we proved. Where? Here. We already proved it's strictly monotone. We need to show it's a continuous. Okay? So we need to show that F inverse is continuous. F inverse is continuous. Suffix fix y0, fix a point in the f of I. Then choose epsilon greater than 0. Choose arbitrary epsilon greater than 0. So again, we assume F inverse is strictly decreasing. Strictly decreasing. F inverse is strictly decreasing on Fi. Strictly decreasing on Fi. Okay, so if y0 is not a right-hand point, of Fi, if it's not a right-hand point, then x0, which is F inverse of y0, is not a left-hand point of I. You have to switch it. Remember that it's we will assume this is strictly decreasing. If F is not right-hand point, the F inverse is not the left-hand point. Okay? So there is a epsilon 0 greater than 0 such that it's not left-hand point. You can do subtraction such that epsilon 0 is going to be very small, and x0 minus epsilon 0 is still inside I. In the book, remember that if you compare this with the textbook we assume it's increasing, so it's on the right side, so you can add. Now we are talking about decreasing. On the left side, you can subtract. Okay? You can do the subtraction. Okay, so you have x0, this one. x0 minus epsilon 0 is still inside I. Then set delta be fx0 plus minus epsilon 0 no, this one. Yeah, fx0 minus epsilon 0, that's minus fx0. Remember, f is a decreasing, strictly decreasing function. This one is positive. Smaller input give you large output. This one is positive. Okay? And suppose that this is a y minus y0. This is y0. It's less than dot, greater than 0. Right? It's greater than 0 and less than dot. Every point. Okay, and this delta implies that this y between y0 and y0 plus delta, right endpoint, you can add a little bit. Which is f of x0 plus sorry let me see, minus. Let's just be careful about this writings. We're talking about the decreasing case. This x0 minus epsilon 0, x0 minus epsilon 0. This is from this definition. Okay, so when y is between these two things, when y minus y0 satisfy this condition, when it is very close to y0, then y will be between this case, right? We add y0 for 3 sides, we have such stuff, and let x be f inverse of y. X be f inverse of y. This implies you see, f y0. Remember, it's a f y0. You apply f to this part. It is less than. Well, let's see what we have. We apply f. No, this is fx0. It's not fy0. fx0. My bad. fx0, which is y0, less than fx, which is y, less than f of x0 minus epsilon 0. Right? We have this. And f is strictly decreasing. F is strictly decreasing. This condition implies x the other way, x0 minus epsilon 0. You have to flip it, right? And this is all of them are inside I, and this implies x minus x0 is greater than negative epsilon 0 and less than 0. Right? Greater than negative epsilon 0 and less than. And epsilon 0, we said epsilon 0 is less than epsilon, so it's greater than negative epsilon. It's greater than negative epsilon. And x, where's x? X is f inverse of y, f inverse of y0. So we have this, right? So what we have for every epsilon, we can find, for every epsilon, we can find a delta such that whenever y minus y0 is less than delta, f inverse of y minus f inverse of y0 is greater than negative epsilon. Greater than negative epsilon. Alright? And this means that f inverse of y is on the right side. F inverse of 0 plus the right limit. You see here, it's the right side. F inverse of y0 plus exists and equals to f inverse of y0. So by this way, we can only discuss the one-sided limit. We can only discuss the one-sided limit. Here, this implies it's a right side, minus y0 is a greater than epsilon, greater than delta. Y minus y0 is greater than delta, so we get f inverse of a y0 plus the right side limit, even though here's a greater than negative epsilon. This implies not equivalent, but it implies f inverse of y minus f inverse of y0 is going to be less than epsilon, right? Okay, so we spend such long time to prove it has a right limit equal to self, and similarly we can show that f inverse of y0 left limit is also equal to f inverse of y0. Okay? If y0 is not a left-hand point, of fi. If it's left-hand point, there's no left limit. Okay, so you prove that the right limit, the left limit, if they exist, if they are reasonable, they both exist equal to f inverse of y0, so f inverse is continuous on the fi. F inverse is continuous on the fi. Okay, so that's the proof. The proof is not that it is standard, but it's not that standard, because usually when we show something is continuous, we will directly say for every epsilon there's a delta such that when fx minus when x minus a is less than delta, ops value x minus a is less than delta. So given epsilon, there exists a delta such that for all x minus a, this implies fx minus fa is less than epsilon. So this is the standard proof. But you see here, there's a one minor thing for this standard general proof. It's because of this case. This situation, it contains x greater than a and x less than a. For greater than a and less than a, you have both cases. You cannot apply, cannot be connected to monotonicity. Monotonicity, we need one is greater than the other one. That's just a case. Or one is less than the other one. If we discuss that, we can only study one-sided limit. That's a reason for this proof we use one-sided limit instead of a regular two-sided limit. But it doesn't matter. You prove one direction, the other direction. The both direction has more or less the same conclusion steps. So try to do this similar argument. Try to do this similar argument. See if you can really get it. Okay? Okay, very good. We finish this proof and we will continue in the next video. Thank you.